Hello everyone, welcome back. So today we'll take up some problems from the book Pathfinder. Okay, so this is first problem and this is question 25 from the CYU section of rotation. Okay, so in this question we have two identical uniform cones A and B that can rotate freely about their fixed central axis. Okay, so the axis that they're talking about is going to be horizontal in this case. Okay, and now if the cone A is rotated with a constant angular velocity of omega A. So omega A is given to be constant. Then the question is how much angular velocity will the cone B ultimately acquire due to friction between the cones? Simply speaking, the rotation of the cone A about this axis will make cone B also rotate, right? So they're saying after some time has passed, cone B actually acquires a steady state angular velocity. So that omega B is what we have to find, Okay, so that is the question. So now let's draw a diagram. Okay guys, so this is the diagram of the situation. So if you curl your fingers in the direction of the rotational motion, that will give you the direction of omega vector. So from the side, the points on the cone will rotate like this. So if the upper cone is rotating in this fashion, it will make the lower cone rotate in this fashion, right? So this guy's omega vector will be towards the right. So let's mark it. So omega B will be in the rightward direction. So it will look, so observing from the right, we'll see the cone rotating in the counterclockwise direction. Okay. So that's how the rotations are. Okay. So now we have to pay close attention to the line of contact. Okay. So before we begin with that, let's mark down the velocities of points on the upper cone and the lower cone on the contact line. So these points lying on the upper cone. Okay, so all these points that are lying on the upper cone, right? These points will have an outward velocity, which I'm representing with the dot sign. Okay, and even the lower cone also has speeds in the outward direction for the contact line. Okay, so now why are we talking about the velocity vectors at this point? Okay, so I'll explain that with the help of an example. So let's say we have a plank that is moving on the ground with some velocity, let's say v1. Okay, and let's say the ball is moving with a speed of v2, and say the coefficient of kinetic friction is mu. Now, if I ask you in which direction is kinetic friction acting on this ball, the answer to that will depend on v1 and v2. Okay, say for example, if the plank is moving with speed of 10 meter per second and ball is moving at a speed of 5 meter per second, okay, then plank is moving faster. So if the plank is faster, what friction tries to do is kill the relative motion. So basically friction will try to bring them to the same velocity values, right? Kinetic friction will act on the ball in the forward direction and it will decelerate the plank till the moment their velocities equalize. Now, if V2 was faster, then kinetic friction will decrease its speed, right? So in short, if we have a particle that is slipping against a surface, then the direction of friction on the particle depends on if it is moving faster or slower. If it is moving slower, then friction will try to accelerate it. And if it is moving faster, then friction will try to decelerate it. So that's the reason why we drew this picture, because with this diagram, we can kind of get an idea of the magnitudes of the speeds. Okay, so here one obvious thing is that at the axis of rotation the speed is 0, and as we move further and further away, the speed of the points increases. So this point has the highest magnitude of speed. So and it's the same for the upper cone as well, right? So let's name this end as A and this end as B. Okay, and let's give the cones some name as well. So this is A and the bottom cone is B. Okay, so one thing is pretty straightforward, guys. If we look at the contact points close to this end A, the speed of the cone B is greater, right? Because so basically this blue dot over here, this has a greater magnitude of velocity. And as we move further away and reach this end over here, the velocity of this pink dot is greater because it is further away from the axis and the velocity of the blue dot is 0. So basically what's happening is as we move along the slant height, the velocity of B is increasing and the velocity of A is decreasing, right? Now the radius was given to be r. Okay, so let's try to mark the velocities at the ends. So the velocity of this edge point, we can write it as omega A multiplied by r, because the distance from the axis is r and the angular velocity is omega A. And here the velocity of edge B is 0, right? So the velocity of this point is 0. Okay, and exactly the same way the velocity of this point is omega B multiplied by r and the velocity of this point is 0. So we go from 0 to omega AR and 0 to omega BR when we move along the slant surface. So now I'm making a claim, guys. So there is going to be some intermediate point, Okay, so let's take this particular point over here and let's drop a vertical line. Okay, so, okay, and let's say this point that I chose is at a distance of x naught from this vertex B. Okay, so this distance I'm saying it is x naught. Okay, and the contact points are this red point and this red point. Okay, and let's say this height is y naught. Then the velocity of the first edge point, right? Okay, so let's call this point as a dash and let's call this point as b dash. So the velocity of a dash, we can easily write it as omega a multiplied by y0, right? And the velocity of edge b dash, we can write it as omega b multiplied by, now is this distance over here, right? It is actually equal to r minus y naught. Now why is it r minus y naught? Because remember guys, these were actually touching each other, right? I separated it out to show the velocity vectors. So if they were touching each other, then the distance between their axes is also equal to the radius, right? So if that's not clear, we can separately draw it. So these are the axes, right? And the distance between them will be equal to the radius. Okay, so if these two are the axes and this distance is y naught, then this distance will be r minus y naught. Okay, so that's the reason why. Okay, so this distance over here is r minus y naught, so we can say it is omega b times r minus y naught. Okay, so now I'm making a claim that this is a special point in which the velocity of a dash and velocity of b dash are equal. Okay, so we can say that omega a times y naught equals omega b times, why does va dash have to be equal to vb dash for some particular point? That we'll try to answer at the end. Okay, so basically now we are going to use the logic that we used in the Planck and particle problem here. So imagine that v2 and v1 are equal for a second. So if they're equal, then there won't be any kinetic friction, right? Because there is no relative motion. Okay, so when it comes to judging the direction of kinetic friction, we have to just observe who is moving faster. Okay, so basically we'll use the logic that to judge the direction of the kinetic friction, just observe who is moving faster. Fk will try to slow it down. Okay, so if v2 is 10 and v1 is 5, then v2 is moving faster. So Fk will try to slow it down and it will try to accelerate the Planck. Okay, and that's the reason why we figured out this special point over here where both their velocities are equal. Now when they're equal, there won't be any friction acting at this point, right? Because there is no relative motion. Okay, so basically at this point a dash and b dash, their velocities are equal. If we move towards the right of a dash, then the velocity of a will decrease, right? Because it's now closer to the axis. So basically if we consider all the points to the right of a dash and b dash, the velocity of b dominates the velocity of a. Okay, why? Because these points are further away from the axis, right? So for example, if I take this particular point x over here and the corresponding point x on the cone A, this point has a larger velocity than vb dash, right? And this x point has a smaller velocity than va dash. And va dash and vb dash were equal, which means this x point has a greater velocity than this point. So in short, if we move towards the right, these blue dots have a larger velocity as compared to the corresponding pink dots. Okay, and by similar logic, if we move in the downward direction, the pink dots have a larger velocity as compared to the blue dots. So let's basically write it down as a note. Okay, so what's the idea? To the right of B, the blue dots are faster, and to the left of B, the pink dots are faster. Okay, so now let's try to draw the kinetic friction diagram for the lower cone. Okay, so this is the bottom cone over here. Now we're just going to mark the kinetic friction forces. Okay, so let's say this is that point B dash that we were earlier talking about. X coordinate was x naught and the y coordinate was r minus y naught, right? So now towards the left of B dash, the blue dots were slower, so friction will try to support it. So the friction will be in the dot direction here. And similarly to the right, the blue dots were faster, so the friction will try to oppose it by acting in the opposite direction, right? So this is how the diagram is looking like. Okay, so this is the friction diagram and this is the velocity diagram. Now once we figured out the magnitude of the friction forces, now the logic is that if omega b has attained a steady state velocity, it means that the net torque about the axis of rotation must be 0, right? Because that's the definition of the steady state. The alpha has to be 0. So the torques due to these dots and the crosses should cancel each other out. Okay, so first let's find the torque due to the left part. So this, if you observe, is the supporting torque. If you observe r vector cross the force vector is along the axis, right? So this is the torque that is along the direction of omega. So let's try to calculate that first. Okay, for this, so let's say this angle of the cone is alpha. Okay, so basically we'll move along the slant of the cone. Let's say we moved the distance of z and we took a small element whose length is dz. Okay, we'll calculate the torque of kinetic friction on this dz element about the axis of rotation. We can write it as mu times the normal reaction dn acting on this point, right? And dn is the normal reaction that the upper cone exerts at this location. Now about the normal reactions, they have given us an information. So they're saying they are pressing against each other uniformly on their entire tapered length. So that normal reaction throughout this contact line is uniform, meaning if you were to define a quantity, normal reaction per unit length, just like mass per unit length, this is going to remain a constant. Okay. So let's say the normal reaction acting per unit length on the slant height is some lambda. So we can write dn as mu lambda dl dz. Okay, because the length of the element is dz, so we can write it as mu lambda dz. So this is the small dk kinetic friction, df kinetic friction acting on this dz element. So now for the torque we need the y coordinate as well. So the d tau is going to be mu lambda dz multiplied by the momentum, so which I'm going to write it as z sine alpha. So this becomes mu lambda z sine alpha z dz. Okay, so now we'll integrate the z coordinate from 0 till our b dash point, right? And what is the z coordinate? I'm going to write in terms of the y coordinate. So in terms of the y coordinate, okay, so for a second I'm going to call it as z b dash. Okay, so basically z b dash I can also write it as r minus y naught divided by sine theta. Now this is the positive torque, right? Now let's calculate the cross torque. The calculations are going to be exactly the same. So it's going to be mu lambda sine alpha z dz. But now the limits are going to change. The limits will be from zb dash, right? Because we are starting from this point now and we'll end till this point. Now, what is the z coordinate of this point? Well, we know the radius is r, right? So this z is going to be r upon sine alpha. Final y coordinate is r upon sine alpha. So now let's just equate these two torques. So the mu sine alpha gets cancelled out and we'll get r minus y naught upon sine alpha squared equals r upon sine alpha squared minus squared. So the sine alpha we can take it out from the denominator, and after doing a bit of algebra we'll get y naught as this particular value. Now once we have y naught, we can substitute it into this equation over here to find out omega b, and after calculation it will turn out to be root 2 minus 1 omega a. Okay, so that's the answer to this question. So if there was also a question, what is the work done by kinetic friction? What is the work done by kinetic friction on the cone B? Then it will be the change in kinetic energy of the cone B, right? Because there is no other force doing any work on the cone B other than kinetic friction. So the work done by kinetic friction will be half I about the main axis. So this is 3 by 10 mr squared times the omega final squared. So this will give you the final work done by kinetic friction just on this cone. Okay. So yeah, that was the discussion of this problem. Now let's move to the next one. Okay guys, so this is a paragraph problem from the chapter Newton's laws of motion. So we have a horizontal conveyor belt here. So it's lying on the xy plane and it is moving at a constant speed of 3 meters per second. A small disk enters the belt moving horizontally with a velocity of 4 meters per second. That is perpendicular to the velocity of the belt. Okay, so basically from the top view, the belt is moving in the x direction and the disk enters in the y direction, and their speeds are given. Now the coefficient of friction between the disk and the belt is 0.5. Okay, so then the question is asking the trajectory. What is the trajectory? What is the minimum width of the belt so that the disk always remains on the belt? And what is the minimum speed of the disk relative to the ground? Okay, so let's discuss these one by one. Okay, so this is a situation given to us. Now guys, obviously we can clearly see that there is relative motion between the disk and the belt. So obviously there will be kinetic friction acting on the disk. So now in order to judge the direction of kinetic friction, we'll go into the frame of the belt. Okay, so if I choose the frame of the belt as my coordinate system, then the belt itself comes to rest and we have to subtract the velocity of the belt from each of the masses. So we'll reverse and add the 3 meters per second onto the disk. Okay, now this is what the velocity of the disk is with respect to the belt frame. So if you're sitting in the belt, you will observe the disk to move along the resultant of this velocity vector. So let's mark this direction with dotted lines. So the disk is going to move in this direction with respect to the belt frame. Okay. Now why are we talking about the question in the belt's frame of reference? The answer is it's because it makes it easier to judge the direction of kinetic friction. The resultant of 4 and 3 is 5 meter per second. So I'm going to erase this for a second and call this as 5 meter per second. So now it's very easy to judge the kinetic friction direction because it will be just opposite to the 5 meter per second, right? Force of Fa. So the kinetic friction force acts in this direction. Okay, so that's the reason why the belt frame is useful here, because we can easily judge the direction of friction. Okay, and we know that friction force is a real force, right? Which means these forces are frame independent. So now even if we go back to the ground frame, the direction of Fk will still be the same. But if we go back to the ground frame, then the velocity vector is not 5 meter per second anymore. The velocity vector is still going to be the original 4 meter per second that we earlier had, right? The 5 was because we were in the frame of the belt. Okay, so basically if we have to judge the FBD in the ground frame, it will be a disc moving in the y direction and a friction force acting on the disc in this particular direction. Okay, so if we read the first option, they're asking us about the trajectory. Okay, so relative to ground, is it a parabola or a straight line? And the answer to that is, we can see that the velocity vector and the acceleration vector, so the acceleration vector will be Fk by m, which is basically in the direction of Fk itself. So okay guys, so whenever the velocity vector and the acceleration vector have some angle between them, which is not 0 or 180, and the acceleration is a constant, meaning the direction of the acceleration doesn't change, then the particle's trajectory is going to be a parabolic trajectory. Just like in the case of a projectile, right? When we learn the case of projectile, we project it with some velocity v. And here the acceleration vector is a constant vector which is in the downward direction. Okay, so this is something that we didn't discuss. So in the going back to the frame of the belt, we'll observe the 5 meter per second and Fk. So here it will be just a straight line motion, right? Because the velocity and the acceleration are anti-parallel. So this will be just a straight line motion. So we can answer this question directly. So it is a straight line relative to the belt, and it is going to be a parabola relative to the ground. So basically imagine this Fk as gravity and this as the velocity of projection. So it'll move something like this, right, in a parabolic fashion. So yeah, that's a little bit about trajectory. So the answer will be B and C. Now we have to talk about the minimum width of the belt so that the disc always remains on the belt. Okay, so now what's the width? So this is the width of the belt. Let's call it as W. So they're saying, what is this W? What should be this W so that the disc doesn't fall off? Okay, so this is pretty intuitive. So if we keep the belt pretty small, there might be some case in which the velocity is so fast that it falls off the belt, right? Okay, so now you guys can imagine. So let's go back to the belt frame once again. So now we can easily imagine that the limiting case will be when relative to the belt, the disc just barely comes to rest by the moment it reaches the end. So we know the trajectory is going to be a straight line. So we want the disc to reach this particular point. Let's call it as point A. So this distance over here is W. Now as the disc actually started from this particular point over here, right? So let's try to figure out this angle theta. Now remember guys, the vertical velocity was 4 meter per second and this component was 3 meter per second. So if this angle is theta as well, then we can say tan theta is 3 by 4. So what is the length of the hypotenuse of this triangle? It will be W divided by cos theta, right? So let's call this point as B. So the length of AB is W divided by cos theta, which is W divided by 4 by 5. So 5W by 4. So the distance it has to cover is 5W by 4. Its initial speed is 5 meter per second and its acceleration is Fk by m. So acceleration is minus Fk by m, so which is minus mu g, which is actually minus 5 meters per second square. So now we can apply v square equals u square plus 2as. So finally we want it to come to rest. So v is 0, u is 5 meter per second, so u square is 25 minus 2a times the displacement 5w by 4. So after solving we get w as 2 meters. So if we choose w to be 2 meters, then the disc comes to rest relative to the belt at the edge point. Okay, so if the width is anything greater than 2 meters, we are fine. So the answer to this question is the minimum value should be 2 meters. Okay, now let's talk about the minimum speed of the disc relative to ground frame. Okay, so now we have to go back to the ground frame. So let's redraw the ground frame picture once again. Okay, so I'm just going to write the acceleration vector here. So this is 5 meters per second square and we know this angle theta. Okay, so tan theta was 3 by 4. So in the ground frame, once again, the velocity vector was 4 meters per second in the j direction. Okay, so this is the picture that we have. 4 meter per second in the I cap direction and 5 meter per second square acceleration in this particular direction. Okay, so now basically, as we discussed earlier, this is just a projectile motion, right? So what do we do to make this 5 meter per second square in the downward direction? Just like in the case of a projectile, all we have to do is take this board and rotate by the angle of theta, right? When we do that, so if we take the belt and rotate it by theta, then this will become 5 meter per second square in the downward direction. Okay, and 4 will rotate in the clockwise sense by theta. The 4 meter per second square has rotated by an angle of theta. Okay, so now this is just like our conventional projectile motion problem, right? And for the projectile motion, we know that the minimum velocity occurs at the topmost point and its magnitude is v cos theta, but here the angle is with the vertical, right? So this is going to be v sin theta. Okay, and what is the magnitude of this? This will be 4 multiplied by 3 by 5, which is 12 by 5 or 2.4 meters per second. Okay, so this is the minimum speed that we'll observe in the ground frame. So the answer to this part is 2.4 meter per second. Okay, so there is another slightly nice looking method for finding the minimum speed as well. So I want to discuss that as well. So okay, so for that, we know that the velocity vector, so the velocity vector was 4 meter per second, acceleration was 5 meters per second square. Okay, and this angle was theta. Now guys, we know the final velocity vector is the initial velocity vector plus a vector into t, right? This is what the equation of motion is, right, for constant acceleration. So if I want the final velocity vector, I have to pick the initial velocity vector and add at vector to it. So the initial velocity vector is 4 meter per second, right? And the second vector that I have to add is at, or in this case it is 5 multiplied by t. But here the problem is t is actually a variable, right? So the direction of this phi t vector is fixed. It is making an angle of theta with the vertical, but the length will depend upon the time. So as time passes, the length will increase. So what I'm going to do is I'm going to draw a dotted line which makes an angle of theta with the vertical. So this is the direction of at vector, but the length will depend on the time. Okay. So let's say at some arbitrary time, this is at vector. This is my 5t vector. Okay. So if this is u vector, this is at vector, then the resultant by triangle law, this is the final velocity vector, right? So now what are the constraints? So the constraint is that the 4 meter per second, the length of this vector is a constant, right? Because this is a constant vector. This angle theta needs to be constant. We cannot change this angle theta. The only thing that we can modify is the magnitude of this phi t vector. Keeping that constraints into mind, we can visually see that the magnitude of the final velocity vector, it is maximum when it is normal to the phi t line. So let's draw it with a pink line. So this is the velocity in which the final speed is minimum. So the phi t vector in this case will look something like this, and they'll form a nice right triangle. Okay, and we can directly see that the v min is actually 4 sine theta from this right triangle, and that is basically what we got here as well. Okay, so yeah, this is the vector triangle method to do this. So yeah, these two methods are much better than just breaking down this acceleration into x and y and solving it. That will take a long time. Okay, so now let's move to the last question. Okay, so the last question is from Kinematics, and this is question 21 from MCQ. Okay, so in the question, we have a particle that is moving with a constant speed on a circular path of radius 4 meters. So the particle A's motion is pretty simple. The particle B moves on a straight line coinciding with the diameter of the circular path, maintaining a constant distance of 4 meters from the particle. So let's draw the diagram first, right? Let's say this pink line represents the trajectory of particle A. Let's draw a diameter to this, and let's draw a diameter. And let's draw the diameter of this circle. The particle is somewhere on the circle. The radii of the circle is 4 meters, and it is moving with a speed of 2 meters per second. Okay, so this is the situation given to us, and the particle B actually is constrained to move along the diameter. Okay, but if you observe in the question, so this is the slightly tricky part. So let's say the particle B is somewhere over here, right? They have mentioned that the distance between these particles is also 4 meters. Now this is actually not possible. Okay, why? Because if you join these two lines, right, and if you drop a perpendicular, it's clear that this length over here is less than 4 meters, right? In fact, you can take any point on this horizontal line. The distance between the two red dots will either be greater than 4 meter or less than 4 meter. It will only be exactly equal to 4 at the center of the circle. Okay, which could be a case, but that's not the question that they're trying to ask, right? They're saying that the particle B actually moves. So if it is moving, then it cannot just stay at the center. So actually what's happening is, if you read the question once again, it is said that the particle moves on a straight line that coincides with the diameter of the circular path. They didn't say it moves along the circular diameter, right? So basically, let's elongate this line a bit. So the particle B is actually somewhere over here. So the particle B is going to be somewhere over here, such that if you join the two particles, the length is going to be 4 meters. Okay, so this is how the diagram is looking like. Okay, so now I'm going to hide the circle with some dotted lines. Okay, so now I'm going to call this angle as theta, right? So the omega of the circular motion, which is d theta by dt, this we can easily write as the velocity of particle A, which is 2 meter per second, divided by the radius 4. So this is going to be 0.5 radians per second, right? Now I know the particle B is constrained to move along the diameter or along the x direction. So let's just call this as x direction, which means which means to figure out its velocity, all I have to do is define its position vector, which let's just say its x coordinate is x. X we can easily determine using, if this angle is theta, then this angle will be theta as well, because these two side lengths are equal, right? So the base of this triangle is 4 cos theta plus 4 cos theta, which is 8 cos theta. So if I want to figure out the velocity, I'll just have to differentiate this. So it'll be minus 8 sine theta d theta by dt, which is 0.5. This turns out to be minus 4 sine theta. Now the reason for the minus sign is because the velocity vector of the point is in the minus x cap direction, and that is pretty intuitive, right? If the particle moves to the right, this length will actually increase in this situation. So the magnitude of velocity, we can write it as 4 sine theta. So now in the first question they're saying what is the maximum speed? It is 4, so option A is correct. And then they're saying the maximum acceleration. So again, acceleration, as it's just a 1D motion, its acceleration is just going to be the double derivative of x, right? So this is going to be 4 cos theta d theta by dt, which is 0.5, which is going to be 2 cos theta. So the maximum acceleration will also be 2 meter per second square. Now they're saying during one revolution of A, distance traveled by B is 32 meters. Okay, so for this question, let's say the particle A starts from this particular point. Okay, and obviously if the particle A is over here, then the second particle will be somewhere over here, such that this distance is 4 meters, right? Now as the particle continues to move in the circle, what happens when it reaches the topmost point? So when it reaches the topmost point, the other particle will have to reach the center of the circle, right? Actually, I'm going to draw the second particle with black dot. So now the second particle is over here at this instant. And when the red dot reaches this particular point, now the black dot must have reached this point, which is at a distance of 4 meters from the red dot. So how much distance did it cover for half the oscillation? So it covered 4 meters and 8 meters for the diameter plus 4 meters. So it's actually 16 meters, right? So for half oscillation, it's covering 16 meters. So for the full oscillation, it will cover 32 meters. So option C is also correct. Okay. Now they're saying in option D, they're saying the magnitude of the modulus of the velocity of a particle relative to the other is a constant. Okay, so for this, we can just break it down into Cartesian coordinates. So if I draw the axis for the 2 meter per second, so this angle is theta, right? So the velocity of particle A is going to be 2 cos theta j cap minus 2 sine theta I cap, and the velocity of particle B is equal to minus 4 sine theta I cap. So if I want to write the velocity of A relative to B, it is going to be 2 cos theta j plus 2 sine theta I. So if you take the modulus of this vector, it will just be 2 meters per second. So which is actually a constant. So option D is also correct. Okay, so this there is also another intuitive way to look at this option. So if you, let's say, observe with respect to this guy, obviously if this length is a constant, the particle A can only have a velocity in the perpendicular direction, right? I'm saying with respect to the particle B. And now we also know that this line over here makes an angle theta with the horizontal, right? So its velocity vector will be in this direction, perpendicular to it, perpendicular to the line AB, and its magnitude will be 4 multiplied by omega. And omega is d theta by dt, and that is half. So if you do it, you'll get the answer as 2 meter per second. Okay. So yeah, that was it for this video, guys. If you have any doubts, you can comment down below. And if you enjoyed the video, please do like, share, and subscribe. And that's it. Thanks for watching.